So this is Andy, I'm Shashwat, and the goal of our project was to have NuPIC predict the orbit of a satellite. So what we did was, well, actually, let me give you some background on how people track satellites today. It's kind of the same way it's been done since like the 60s and 70s, and actually like pinpointing a satellite out in space is really difficult. So people like NORAD and the military, they set up massive arrays of radars that are like gigantic, over acres, and they just like beam into space like at different places on Earth, and they're able to detect things like, oh, that's the ISS, oh, that's a rock, oh, that satellite has been dead for like the last 20 years, whatever. So they basically can identify these objects and identify the position and velocity, and they publish that fairly regularly, and they give it out to people saying, hey, at this time, we saw this satellite moving like this over here. So then what everybody else does is they don't have radars and stuff like that, so they take that information, and there's this algorithm, it's called the SGP4, and there's an SDP4. I don't really know what it stands for, but what it does is it's a numerical method that takes that information and just basically like ticks it forward and says, based off Kepler's laws, okay, if you saw this over here with this velocity, then now it should be over here with this velocity. And it tends to be pretty accurate, but NORAD has to keep publishing new element sets for the satellites, because within a week or so, it tends to start drifting because actual space is like really complicated, and they fly around, and like it's not really as predictable as the math would make it seem. So that's for like most satellites. With satellites like the ISS, they're active satellites, so they can like move up and down, and they have little jets on them. They like scoot around and do weird things. So their position is even more unpredictable. So NORAD actually updates the ISS like 3 or 4 times a day, so they keep that up to date. Now, of course, the ISS is like super advanced and modern, and they have like multiple redundant GPS like things on them, so they know where they are. But this is the method that ham radio enthusiasts use to talk to like the really simple CubeSats and the HamSats and stuff like that. So what we did was we took the ISS and we took a bunch of these element sets, and we propagated the path of the ISS over many different element sets so we could get a very smooth and as accurate as possible model of the ISS's path over several days. And we gave that to Subutai's NuPIC harness, and basically we're looking for anomalies and hoping that NuPIC would learn and settle down and kind of predict the circular or elliptical motion of the satellite. So from a single point on Earth, a satellite appears to like kind of like move it has like a phase shift. It doesn't rise and set at the same place. That's because the Earth is rotating. But if you were to look from space and have the Earth be rotating in a separate frame from you, the satellite is actually moving in a very, very like elliptical, regular way. So we were hoping that NuPIC could pick up on that and then predict the satellite's motion. And with satellites like the ISS, which can move on their own, they may have routine, it's Tuesday, let's drop down a bit, or it's Wednesday, let's go over here. So hopefully NuPIC can pick up on that as well. So what we did first was we tried to get the anomaly. So this upper graph here is the anomaly, and this is just the X direction of the satellite. So the satellite oscillates in the X direction, and over here at the very end, we injected an anomaly. Andy just threw some like crazy numbers in there, and you can see that NuPIC kind of tripped out. It was like, that's not normal. Although it seems to be tripping out pretty regularly, here it tripped out a little more. So we think it's learning. So we got this, and we're pretty happy. So we decided let's actually have it predict where the satellite will be. So before I show you the prediction, let me show you what a normal satellite orbit looks like. It's very, oh, it's lagging right now. It's very smooth. You can see that it doesn't tend to vary that much. So we asked NuPIC what it thought the satellite would look like, and it's not as smooth. But it kind of got the idea. Like, it's still going in a circle. I think it takes a nosedive at some point along this path. But this is just this is like 90 minutes worth of the ISS's flight. So, not bad. I think the next thing we would do is try and get as much data, like, to be rendered here, so you can see the orbits and multiple orbits and see what it was doing.
So 90 minutes is how much data? What's the sampling rate?
Sampling rate for NuPIC was once a minute.
That's 90 minutes.
Yeah. No.
Well,
actually, if I show you over here, we taught NuPIC with like 100 or 800. Actually, no. We only took the first 800 of these after we injected the anomaly. We actually taught it over like 10,000. So we taught it for a while, and then we just took one snapshot of that and rendered the predictions for that.
Something odd here. I mean, it's not clear why you're having that anomaly. Sorry, Matt.
The spike every time.
Yeah, why is it getting an anomaly spike here every time? That doesn't make sense to me. Does it make sense?
I don't know, but we've been looking at these sine wave patterns a lot, and one thing is, because it's a memory-based system, it's looking at the patterns and trying to figure out what's happening next. You probably quantize the sine wave, and you discretize it with a certain way. And I don't know if your discretization is divides evenly into the period of the sine wave.
Oh.
If it doesn't, then every time you go in, it's actually getting a different set of inputs. Eventually will work out, but it could take a long time if you don't. And that was one of the things we had to do in the sine wave tutorial that Matt put together to get that stuff working well. So there's, it's a little tricky, but that could trip it up potentially.
How many samples per
the thing there.
What was that?
How many samples per period is it?
90? It's about 90 per orbit.
Okay.
Maybe like 90 to 100. And we did one every minute, so.
Okay. The other possible thing is that, I don't know if you swarmed over this set.
We did not. We just used your...
You just used the
run
default
along
parameters,
code.
so...
We played with all the model parameters,
Yeah.
but we didn't really change the window size that much. We didn't change the size of the buckets.
Okay. Yeah, because definitely the anomaly score should end up looking a lot better than that.
Yeah, if you
do that.
With our 10,000 data points, the anomaly score ends up just drifting down, ends up just hitting 0 and pretty much flatlining at 0 in the end. But that's after many thousand.
Okay. And then if you add the anomaly after that point, you should see a very
Yeah,
clear...
it does spike up.
Oh, we should have
like
we should have
one or
plotted
two
that.
data points. So it's very hard when you're going over 10,000 data points to see that one tiny spike at one data point of 1. So.
Yeah, it seems that I'm pretty sure that the big spikes are when you cross 0, and the smaller spikes are when you change direction at the top and bottom. Certainly seems to be most of them.
Yeah, and that could be the discretization issue. Yeah.
All right, well, yeah, thank you.